Hi, in this first chapter, we will be talking about kinematics. So, kinematics is the study on the motion of objects, and we want to describe how objects move over time. So, in order to do that, we need to understand three basic pieces of variables, which is the position, velocity, and acceleration. And we need to know how these three variables change over time. So if we know all this and we know all the behavior of these three quantities, then we should be able to effectively describe the motion of these objects, and most importantly, we should be able to make predictions on where or how fast the object is moving at any future time. Suppose we wish to drive from one city to another, say Ipoh and Kuala Lumpur. The distance between these two cities is approximately 200 kilometers. Now, typically the drive would take about 2 hours, so some person doing this in real life would get in the car and while driving, making sure that they are driving under the speed limit, which is around 110 kilometers per hour on the highway. They will find that they will reach their destination approximately 2 hours later. So if we take the total distance to be exactly 200 kilometers and the time taken to drive is exactly 2 hours, we can say that the average velocity of the drive is 200 divided by 2, which is 100 kilometers per hour. So on average, the car has been driving at 100 kilometers per hour, which is consistent with the typical highway speed of 100 kilometers per hour. We can analyze this in a more precise manner by sketching the graph of position versus time. For the car, let's call this car A, driving 200 kilometers within 2 hours. The movement of the car can be tracked on the graph here, like this. Suppose we have another car B that is driving much slower than A. It only reaches 200 kilometers in 4 hours. So the motion of the car that can also be tracked on this graph, and it looks like this. We see that these two graphs have different slopes or gradients. Clearly, graph A has a steeper gradient than B. In other words, faster object has a steeper gradient in the position time graph. This gradient can be easily calculated, and this is the definition of average velocity. We just take the displacement, which is the final position minus the initial position, divided by the time taken. Now, what about cars moving that's not going at constant speed? Take, for example, an object that moves like this. As time moves on, this object moves away from its starting point fairly quickly, then turns back for a while before turning around yet again to go away from the starting point. For a motion like this one, the average velocity will be different depending on which interval you evaluate this. So if you take this interval, you will get a large positive average velocity, positive corresponding to the upward slope, while for this interval you get a negative average velocity, downward slope. Then at intervals like this one, you'll get a fairly flat slope, so you will get a small average velocity. In order to accurately describe motions like these, it would be much easier to assign a value of velocity at every point on its motion. This is the instantaneous velocity. Suppose 2 points are infinitesimally close to each other. In other words, delta t is really small. Thus, the initial and final positions are almost the same point. The average velocity for these two infinitesimally close points is what we call the instantaneous velocity. Mathematically, this is defined by taking the limit where delta t goes to 0. So this is equivalent to taking the derivative of x with respect to t, the process of differentiation. From this reasoning, we have arrived at our definition of velocity. V is the limit where the time interval goes to 0 of the average velocity. We can also equivalently say that velocity is the rate of change of position. So now we know how to calculate velocity from position. Can we do the reverse? What if we are given the function of velocity first and is required to calculate its position? We'll do the opposite of differentiation, which is, of course, integration. Given the velocity as a function of time, we can recover the position by integration. Since v is defined as the derivative of x with respect to t, we can move the dt over and integrate both sides of this equation. Of course, when performing integrations, we would need to know the limits of the integration. So let us suppose that the initial position is x0 at time 0. This gives our lower limits. At some later time t, the object is as x. Working out the limits of integration, we see that the left-hand side is simply the final position minus initial position. In other words, this is the displacement of the object. As we recall from mathematics, integration is the area under a graph. So we conclude that given a graph of v against t, displacement is the area under the vt graph for that time interval. Having the notion of velocity, we can now move on to our final important quantity for kinematics, which is the acceleration. Just as velocity is the change of position over time, acceleration is the change of velocity over time. All the definitions are similar to what we just did for velocity. So in particular, the average acceleration is the final position minus the initial position divided by the time interval. In the same way, the acceleration is just the limit of infinitesimally small time interval of average acceleration. From mathematics, again, we see that this is actually the derivative of velocity with respect to time. Also, since velocity is itself a derivative of position, the acceleration is the second derivative of position with respect to time. Or you can just say it is the second time derivative of x. So our three main quantities of kinematics are interconnected by differentiations or integration, and we can easily get from one to the other by doing either one of these operations.